in the last session. It was exactly on last Monday. On that day only, I was not feeling well, and I tested COVID positive in the last week. Still, I'm quarantined, but now I'm okay after taking rest of 4 to 5 days. So we'll be continuing our next part, that is composition of relation matrices. All of you are able to listen me?
Yes, ma'am.
Okay, thank you. We will revise the relations again. Here we have seen what are the relations. Then here, when we are taking some type of relation between two sets, then that relation R is said to be from set first set to second set. Here we have taken two sets, that is X and Y. So we say that a relation or a binary relation is R is from set X to Y. Okay, and it is a subset of Cartesian product X cross Y. Okay, when we take a Cartesian product of these two sets, it is a subset. I mean, this relation set is a subset of this set. Okay, if the ordered pair is reversed, the relation also changes. Okay, ordered pair is there, means order of the elements in the pair or order of the elements in the particular that pair. It's important because these are ordered pairs. Okay, and then when we say that relation is from A to B, we denote it like this one: A R B, or AB belongs to R, or R of AB. All these are same. These are just the notations for that. Okay, then a binary relation R on a single set A is defined as a subset of A cross A. If a single set is there and relation is defined on that single set, it is a subset of A cross A, means Cartesian product of A with itself. Okay, because those only pairs it will contain which are there making set elements of A with itself. Okay, then for two distinct sets A and B with cardinalities M and N, the maximum cardinality of relation R from A to B is M into N. Okay, cardinality means again what? Number of elements in that set. How many elements in that set it will be? That will be defined by the means counting the elements in that set. But if maximum, how it will be? It will be M into N, where M is the cardinality of A and N is the cardinality of B. Okay, then we saw domain and range there. Then elements of first set are known as domain and elements of second set known as range. Okay, it is this simple words we can say like this, but in while writing in scientific way, what we have to write it like, if there are two sets A and B and relation from A to B is R AB, then domain is defined as the set A such that AB belongs to R for some B in B, and range is defined as the set B such that AB belongs to R for some A in capital A. Capital A is the set A, and this A, small a, is the element of that set. Okay, element of this set. Then we saw this example, and with the help of whiteboard we solved such type of examples. Then we saw inverse of a relation. What this inverse is, if R is the relation from set A to B, then inverse relation of R is from set B to A. Simply it will be written like this. If R is from A to B, then R inverse is from B to A. We have given the relation like 1, 2, 2, 4, 3, 6. It will be 2, 1, 4, 2, 6, 3 like this. Okay. Interchanging X and Y values, A and B values. That's it. It is a inverse relation. Then we saw types of relations are there. Which are there? Empty relation. A relation R on a set A is called empty if the set A is empty. Then full relation. What it is? A binary relation R on a set A and B is called full if A cross B, means a relation contains all the elements of cross product of A and B, then that relation will be known as full relation. Then reflexive relation is there. What is there in the reflexive relation? A relation R on a set A is called reflexive. A relation R on a set A is called reflexive if A comma A belongs to R, holds for every element of A belongs to A. That is, if set A is equal to A comma B, then R is equal to AABB is reflexive relation. Okay, what it is saying that A, that is small a, belongs to capital A, then and that set A is A comma B, and if I take a relation R as A and B, then that relation will be reflexive relation. If it is not there, then that relation is known as irreflexive relation. Okay, reflexive and irreflexive. Reflexive means it is there, means B elements are there, that is known as reflexive. And if those are not there, then that is known as irreflexive relation. Then symmetric relation also we have seen. In that, a relation R on a set A is called symmetric if BA belongs to R, holds when AB belongs to R. Opposite means X and Y values are interchanged, and then also those are included in the relation group. Then that relation group will be known as, then that set will be known as symmetric group. Okay, antisymmetric is what? Antisymmetric is when A is less than B is less than A, it implies that A equal to B, and such A, B are included in the relation, then that relation is known as antisymmetric. If for A comma B belongs to R, B comma A belongs to R is not there in the relation, then that relation is known as asymmetric relation. Okay, then transitive relation is there. Asymmetric we have seen this one, antisymmetric we seen, asymmetric. Now we'll go to transitive relation. What the transitive relation is? If A comma B belongs to R, B comma C also belongs to R, then there must be like A comma C belongs to R. Okay, for all A, B, C belongs to A. Okay, so if relation R is like this 1, 2, 2, 3, 1, 3, okay, on set A equal to 1, 2, 3, then that set is a relation is known as transitive relation. Okay, and what is the last type, that is equivalence relation? If a relation is possessing all three properties, reflexive, symmetric, and transitive, then this will be known as equivalence relation. Okay, then now only we have seen the properties of binary relations, that is reflexivity, symmetricity, and transitivity. Then relation as matrices. Relations can be represented with the help of matrices using 0 and 1, that is binary language. And here what we do is, whenever the elements are, whichever the elements are there in the relation, those will be marked as 1 in the matrix. Okay, here mr is equal to mij. Okay, and mij is what? I is the ith row and jth column. Okay, row and column. Okay, like this, the relation matrix will be there. What is there in properties then? A relation R is reflexive if the matrix diagonals are 1. If these matrix diagonals are 1, then the relation R is reflexive. Then if it is not there, then it is irreflexive. Then a relation R is symmetric if the transpose of relation matrix is equal to original matrix. Means what? So how it is symmetric? If we take the transpose of the matrix, it is same as the original matrix. Transpose means what? Where we take our rows as columns and columns as rows. Okay, that type of matrix is known as transpose matrix. And if original matrix and transpose matrix both are same, then the relation R is known as symmetric relation. Then what the next is, if relation R is antisymmetric, then Mij is equal to 0 or Mji is equal to 0 when I is not equal to j. When I equal to j is there, all these Mij or Mji are 1. Okay, but if this is 0 when I is not equal to j, then the relation R is known as antisymmetric. The next is for join and meet property of relation. The joint matrix M1 and M2 is M1 or M2, which is represented as R1 union R2 in terms of relation. It is known as joint property. And what is meet property? A relation follows meet property, that is the meet of matrix M1 and M2 is M1 and M2, which is represented as R1 intersection R2 in terms of relation. Okay, joint property and meet property both are explained here. Then directed graphs. In this also we have seen, this is reflexive, that is the arrow is coming towards A, from A to A, from B to B, from C to C. So it is known as symmetric. Okay. R is not transitive. What transitivity means what again? If relation is from A to B, B to C, A to C relation should be there, and A to C is not there, so it is not transitive. Okay, Then here also, this point also we have seen there is loop at every node. This loop is there, A to A, B to B, and C to C. Then it is reflexive. It is neither symmetric or nor symmetric, as there is a single edge from A to B. From A to B, it is there. But here, reflexivity is there, but transitivity is not there. And what about symmetricity? Symmetricity is also not there. Okay, so graphs are written like this, in this manner. Okay, then partition of set. Okay, again we have seen this type of example also. The empty set phi has exactly one partition, namely phi. Okay, for any non-empty set X, P is equal to X is a partition of X called trivial partition. Okay, how the partition is there? Trivial partition is there because P is containing elements of X. Okay, and X is the partition. Then particularly every singleton set X has exactly one partition, namely X. Why it would be? Because this is the singleton set. Okay, singleton set means what? Again, only one element is there. Okay, then next is here the example given is 1 2 3. For that we can write it like these 1 2 3 1 2 3, then 1 3 2 1 2 3 and 1 2 3. Okay, then these are not examples of partition. These are not the partitions. How the examples are written, we can see here. 5 set is there, 1 3 in one set, 2 in another set. Is not a partition because one of its element is the empty set. Empty set is not there in the partition of set. Then here partition should be again like 1 2 3 or 1 3 2, like that. Okay, here 2 is occurring twice, so it is not considering it as a partition of a set. Okay, and the last is 1 2 is not a permanent is not a partition of 1 2 3 because none of its blocks contain 3. However, it is the partition of 1 2. Okay, as the set is 1 2 3, only 1 and 2 will not be the partitions, 3 also should be there. So this is not also the partition. Okay, then we saw composition of relations. Here we considered 3 sets. Then R be a relation from A to B and S be the relation from B to C. That is, R is a subset of A cross B. R is a subset of A cross B and S is a subset of B cross C. Then R and S give rise to a relation from A to C indicated by R composite S. Okay, R composite S. It is denoted like this. this hollow circle is there, and that known as composite R composite S. Then here what we have to define is R composite S relation from A to C. If for some B belongs to B, we have A RB and B S C. Okay. The relation R composite S is known as the composition of R and S, and it's sometimes denoted simply by RS. Okay. Then simplifiedly, they can be written like R and S also. And let R is a relation on a set A, that is R is a relation from set A to itself. Okay. Then this one R composite R, the composition of R with itself is always represented. Excuse me. Also, R composite R is sometimes denoted by R cube. Similarly, R cube is equal to R square into or R square composite R, which is also equal to R composite R, and so on. Thus, R raised to N is defined as all positive N. Okay, it is defined as all positive N. Then we saw these examples here, how the x to y and y to z are. Then what we have to find is x to z first. X to z, that is from R1 to x to y, here it is y, R1, and y to z, here it is y, R2. And what we have to do is x to z. For very first stage, we have to take the here from x to z, we have to define the relations. So from x to y, which are the relation is there, that will be defined from y to z, and therefore we will get the answer. Okay. Then what we, firstly we have to calculate is R1 composite R2 and R1 composite R1 inverse. Then how we went for that is this one, we draw the diagram. Then 4 to A to L is there, 4 to A to N is there. So 4L and 4N will be the pairs for R1 composite R2. Same like 5CL is there. So 5L will be there, 5M will be there, and 5N is also there. Then from 6, what are they? 6 to A to L, and 6 to A to N. So 6L and 6N will be there. Then 6C is here. 6CL, 6L we have covered. 6CM. So 6M will be the next pair for R1 composite R2, and 6CN, 6N is covered there. So here 6M, 6N. So R1 composite R2 we have calculated here. Now here you have to take this one. Okay. Here, what is the relation given? means what we have to figure out is R1 composite, R1 inverse. In that case, first we have to again should take the x inverse here, means 4 to A to 4, 4 to B to 4, then 5 to C to 5, 5 to C to 6. Okay, then this one 6 to A, and again 6 to 4 and 6 to 6 is also there. And here 6 to C, it will again 6 to 5 and 6, 6. Okay, all these are the elements of this one, R1 composite, R1 inverse. Then all these are the contents which are already we have discussed. We will go to the new part, is the composition of relation matrices. Okay, what is this composition of relation matrices? There is another way of finding R composite S. Okay, here what we have done is we simply draw the diagrams and then went for the relations that we wanted. Now what it is saying is there is another way of finding R composite S. Let MR and MS denote the respectively matrix representations of the relations R and S. Okay, MR is the matrix representation of R and MS is the matrix representation of S. Okay, now P is what? 2, 3, 4, 5. Okay, 2, 3, 4, 5. Consider the relation R and S on P. Okay, relation R and S on P is defined like this. P is the set 2, 3, 4, 5. How R and S are defined? 2, 2, 2, 3, 2, 4, 2, 5, 3, 4, 3, 5, 4, 5, 5, 3. Same is like S. 2, 3, 2, 5, 3, 4, 3, 5, 4, 2, 4, 3, 4, 5, 5, 2, 5, 5. Then find the matrices of the above relations. Use matrices to find the following composition of relation R and S. Here what we have to again calculate is R composite S. Okay. Now here with the given information, what we have here is the matrices of relation R and S are like this one. Okay, MR is like see here in this slide. R representation with matrices. 2, 2 is there, 2, 3 is there, 2, 4 is there, 2, 5 is there. Okay, and then 3, 4, 3, 5, 4, 5, and 5, 3 like this. 8 elements are there in the R. So 8 times 1 will be there. 2, 2 is there, 2, 3 is there, 2, 4 is there, 2, 5 is there. Then 3, 4 is there, 3, 5 is there. Then 4, 5 is there and 5, 3 is there. Okay. So this one is the matrix representation of R. Same with S. In S, what given is 2, 3 is given, 2, 5 is given, 3, 4 is given, 3, 5 is given, then 4, 2 is 1, 4, 3 is also 1, 4, 5 is also 1. Okay. And now this one, 5, 2 is there and 5, 5 is also there. So here we can count it like 1. To obtain the composition of relation R and S, first multiply MR and MS to obtain the matrix MR cross MS as shown in figure. Okay. Now what we have to perform is, firstly, we have to take the multiplication of two matrices, MR and MS. Whatever the multiplication will be, where the non-zero entries are there in the multiplication, those will be these one are composite as relations. Okay. So what this product of these two matrices comes is to see here the places which are having non-zero element. Okay, 2 2 is there. Okay, 2 2 is there. So what we can write is like it 2 2 is non-zero, we can see here. So we can write 2 2 there. Then for 2 3, is it a 0? No, it is not a 0. So we can write it here. Then 2 4, is it a 0? No. So it is like this one, 2 4. Here, which pairs which are not non-zero, all such combinations are taken for the R composite S. Okay. Simply 2 5 is also not the 0. So 2 5 is also written in this one. Okay. Then 3 2 is there. Then 3 3 is there. Here 3 3. Okay. But we cannot see 3 4 because it is a 0. We cannot consider 3 comma 4. Then if we take 3 comma 5, that it is also non-zero, so we can consider it. Then if we consider 4 2, it will be considered. Then 4 5, it is non-zero, it is also considered. And then the last one is last row, that is 0 0 1 1. So what we can write it here like 5 4 is also the pair of R composite S, and 5 5 is also the element of composite set R and S. Then what next we have to define is R composite R. Then taking the multiplication like MR cross product MR, then this type of arrangement should be there. 2 3 4 5 and 2 3 4 5. Here again we will perform the multiplication of same matrix with self. Then this one what we can take is R composite R 2 comma 2, then 3 comma 2, 3 comma 3, here 3 comma 3 we can consider, and we can consider 2 comma 3, not 3 comma 2. Okay, this answer should be somewhat means it should be mistaken, but here what we have to consider is non-zero values of the places in the matrix. Okay, and those places will be known as their these one. Okay, elements of R composite R. And last is nothing but MS composite MR, that is S composite R we have to perform. In that multiplication of two matrices will be like this, MS cross MR. Okay, This is the composition of relations with the help of matrices. While teaching it to you people, I'm assuming that you know how to perform the multiplication of two matrices. Do you know multiplication of two matrices?
Yes, ma'am.
Then good. Okay, this is the last bit of this unit, that is relations, that is poset and hash diagram. What is there like poset? We can see a poset consists of a set together with a binary relation indicating that for certain pairs of elements in the set, one of the elements precedes the other in the ordering. The relation itself is called a partially order. Okay, partial order. So the name here is partially ordered set. Okay, poset means what? Partially ordered set. The word partial in the names partial order and partially ordered set is used as an indication that not every pair of elements needs to be comparable. Okay, means what it is saying is a partial in the names partial order and partially ordered set is used as an indication, okay, that not every pair of elements needs to be comparable. Means what? These are the partially ordered. Any operation will be taken there, and considering that operation, we are taking the set as partially ordered set. What this poset consists of, we will see again. A set together with a binary relation indicating that for certain pairs of elements in the set, one of the elements precedes the other in the ordering. Okay. Precedes means what again? What here we are considering? Here some order is ahead of the other order, means some of the order is partially ordered, means again we can say if we take the word to word meaning of partially ordered set, then ordering in the set is partially fulfilled. Okay, not fully fulfilled. That is nothing but a partially ordered set. Okay, then it is used as an indication that not every pair of elements needs to be comparable. As those are the partially ordered, they may not be comparable, they may be comparable or they may not be comparable. That is, there may be pairs of elements for which neither element precedes the other in the poset. Partially ordering is there, means sometimes ordering may be here and there. Okay, considering the binary relation there. Okay, what the relation taken is there, that relation will define what type of pairs are there in the elements. Okay, which will precede the other in the poset. Again, when partially ordering is there, depending on the binary relation, the ordering is not that means it may be changed. Okay, that's why it is said that partially ordered sets. Okay, a poset can be visualized, its hash diagram, which depicts the ordering relation. Okay, the these are the partially ordered sets are here taken with the means we can depict them with the help of diagram, and that diagram will be known as hash diagram. Okay. A hash diagram is a graphical representation of the relation of elements of a partially ordered set with an implied upward orientation. Okay, upward orientation means base will be at the bottom, or which is the main core part will be there, that will be at the bottom, and in upward direction other sets will be there. A point is drawn from the element of a partially ordered set and joined with the line segment according to the following rules. Some rules are there for the diagram. If P is less than Q in poset, then the point corresponding to P appears lower in the drawing than the point corresponding to Q. The 2 points P and Q will be joined by line segment if and only if P is related to Q. If P is less than Q, then in diagram, P will be at the lower position and Q will be at the upper position. Okay, because P is less than Q. And if P is related to Q, then and then only relation will be there. Okay, how we will say like this is, we can see here the hash diagram of set of all subset of 3 element set X, Y, Z ordered by inclusion. Okay, inclusion is the operation, binary relation taken here. Inclusion means what? X, Y, Z. In X, Y, Z, how many elements are there? Okay, how many sets are there that we can take? Okay, inclusion, again here we can consider it like as the power sets of XYZ. Why? Because what is included in this XYZ is nothing but the power set of this set. The other sets included in this set is nothing but the power set. So this type of relation is known as inclusion. Okay, ordered by inclusion. This is very important. How they are included, we can see here. Phi is there, null set, and then again in upward direction we are moving. Singleton sets are there, X, set Y, and set Z. Then again combining the relations like this. From X and Y, XY is there. From X and Z, XZ is there. And from Y and Z, YZ is there. Okay. And lastly, containing all these three, what it is there? X, Y, and Z. Okay. It is nothing but the example of hash diagram and poset. It is a poset. It is a partially ordered set ordered by inclusion. Okay. It is a relation taken, or it is a operation taken. It is nothing but the hash diagram of partially ordered set X, Y, Z. Okay. Ordered by the relation inclusion. Okay. Ordered by the relation inclusion. Okay. We can see here the hash diagram of set of all subsets of 3 element set X, Y, Z ordered by inclusion. Sets connected by an upward path like phi and xy are comparable, while x and y are not. Okay. Now phi and xy are comparable. Okay. Phi and xy. But these x and y are not. Why? Because there is no any edges there between x and y. Edge is there between phi and xy. Phi from x, phi from y, and then these x and y are combining to xy. So we can say that phi is comparable to xy, but this singleton x and singleton y are not comparable with each other. Why? Because why it is? Because singleton x is there and singleton Y is also there. Okay. It is nothing but the partially ordered set and hash diagram. Okay. Here it completes our unit. Any difficulties here in this unit? Yes.
No, ma'am.
Okay. So we'll just take a little bit introduction of next unit, that is function. I will open the PPTs. Just tell me up to which unit I have given you the assignment or some questions to write. Yes. Can anybody please tell me?
Second, ma'am.
Second. Okay. In teaching diary, if you are taking it means you are referring the teaching diary of your class on daily basis, you can see in our DMS tab of that teaching diary. I have given you all the PPT links there, and in that MCQs are also there from unit 1 to 3. Okay, please go through that from your teaching diary. 1 to 3 MCQ is written there. Okay.
Okay, ma'am.
Yes, you can refer MCQs from there. And for next MCQs, I'm working on that. Soon I will share that link with you. While ending the unit 4, we complete our section 1. Okay. Here from unit 5, we are going to start section 2. In that first unit is functions. Okay, the very first unit. Excuse me. This is again, as I told you, depending on the third unit, that is sets. First 2 units, those are not that depending on each other or other syllabus topics. But after third, all other units 3, 4, 5, 6, 7, and 8, all those topics are depending on the unit 3. Okay, so in unit 4 also we have gone through that 2 sets are there, and relation is from set X to set Y. Same is here. Functions, this is also depending on unit 3, 2 sets are there, and functions are defined from one set to another set. Okay, same as unit 4, we are going to see function types, then composition of functions and inverse functions. These are the contents of this unit. Today we'll see what is function. In mathematics, a function from set X to a set Y is an assignment of an element of Y to each element of X. Okay, the set X is called domain of the function and set Y is called the codomain of the function. Okay, what the function is? A set X to a set Y. Function from set X to a set Y is an assignment of an element of Y. Is an assignment of an element of Y to each element of X. To each element of X. It is the difference between relations and functions. In relations, a relation was defined. Then only the pairs were there in the relation. How the function is? Each element of Y, an element of Y is assigned to each element of X. Okay, that is the difference between the relation and function. Functions were originally the idealization of how a varying quantity depends on another quantity. For example, the position of a planet is a function of time. How originally they were thought as depending quantities are there. Okay, one quantity is depending on the another, so that will be known as the function. Example what taken is position of planet is a function of time, means time to time planets are changing their position. Okay, or time to time our vehicle is also changing its location. So we or we can define many functions like this. Okay, means velocity is the function of acceleration, and already we have seen in school timing also. Okay, so function is the depending quantity. Okay, it is a varying quantity, depends on another quantity. Means work and time. Okay, that is also comes under this. Means more work, uh sorry, some work is same, but means many people, two people are doing same work in 2 days. Okay, if we take 4 people, then same work will be done in 1 day, like that. Okay, those are also the examples of functions. Some quantities varying depending on the another quantity, that is nothing but the function. The concept of a function was formalized at the end of the 19th century in terms of set theory, and this greatly enlarged the domains of application of the concept. Okay, uh, in 19th century, in terms of set theory, the functions were function concept was formalized, means emerged. Okay, and greatly enlarged the domains of applications of the concept. After that, in after 19th century, it came into the picture. Then a function is most often denoted by letters such as f, g, and h, and the value of a function f at an element x of its domain is denoted by f of x. Okay, function f to the element x is denoted by f of x. Getting? A function is uniquely represented by set of all pairs as x f of x. Okay, x f of x. If we take the pair x comma y, then that y is equal to f of x will be there. It is called the graph of the function. Okay, if we go to draw x and f of x values, then what we do is we are taking graph of the function. When the domain and the codomain are sets of real numbers, each such pair may be thought of as a Cartesian coordinates of the point in the plane. If the sets are real numbers, then coordinates of point in the plane will be there, means both the elements will have natural numbers. Suppose 2, 3 will be there, 3, 4 will be there. And if we go to plot those points in the plane, then it will be the Cartesian coordinates of the point in the plane. Okay, the set of these points is called the graph of function. It is popular means of illustrating the function. The functions are more easily understood with the help of graphs. Functions are widely used in science and in most fields of mathematics. It has been said that functions are the central objects of investigation and in most fields of mathematics. Okay. Functions are the central objects of investigation. If any investigation is to be performed, then these functions are known as central objects of investigation in most fields of mathematics. Okay, it's already 3:30. We'll see the next part in our next session. Okay. 14 participants are there. Who are the two roll numbers? Those want to, those are absent. One is there.
3 or 6, ma'am. Absent.
3 and 6. Okay. 1, 2, 3, 4, 5. Yes, it's there. 5. 6 is not there. 3 and 6. Okay. We'll consider.
2 present, ma'am.
Yes, yes. I can see. Yours is Mallar.
Yes, ma'am.
Oh, yes, yes. I'm just counting. Okay, we'll see next part in the next session. Thank you. Stay home, stay safe. That's really important.